Today in chemical engineering, we're going to use material balances to solve a problem on control volumes and applying the conservation of mass. On the left side of the screen, you can see the problem we're solving today. I'm not going to read it to you, but you should take a moment here to pause the video and read it and understand it before we get started if you haven't so already. So the main things to take away is stream 1 is based on 100 moles. So we have that drawn out here in our diagram. And then in that stream 1, it's 1% SO2, which we also show right here by this mole fraction of 1%. The rest of it is a gas called A. So this gas is A, 99%. Stream 2, we don't know anything other than it's all B, which is shown right there, pure solid in B. Stream 3, we know that it's going to have less SO2 than the gas stream coming in, but we don't know anything about it other than this line right here, that 10% of the SO2 from the stream 1 remains in stream 3. And then stream 4, again, we know nothing other than the fact that the liquid is composed of 0.2% SO2 by moles. So some of the SO2 is going to show up in this stream, and it's going to be 0.2%. So to do a degree of freedom analysis, we're going to look at keep our flow sheet up here, and we're going to look at what we don't know. So we don't know 5 different values, which we've gone over before with the question marks. And the reason we know things like Y3A is because the problem shows that there's only 2 components in each stream. So if you know one stream is 25% something, the other component is going to be 75%. Then we have 3 material balances. So in this problem, there's A, SO2, and B. So those are 3 atomic material balances, or component material balances, sorry. But one of those could be replaced with a total balance if you wanted to. And then we have the 2 pieces of information I talked about before, the SO2 split, the 10%, and then the liquid effluent, that's 0.2%. So if we can get equations for the 3 material balances, the SO2 split, and the liquid effluent composition, then we can solve for all 5 unknowns. So we have 0 degrees of freedom. So doing that, we're going to look at what is the liquid effluent composition. So the composition of a stream 4 is going to be 0.2%. 0.002 moles of SO2 per mole of a whole thing. So we right away we solved one of the unknowns. Then we look at the SO2 split. So it's saying 10% of the SO2 that's in stream 1, which is this value, is equal to the SO2 in stream 3, which is this value. So that's how much moles are in stream 3 times the mole fraction. And then we can look at a balance on A. So we're only looking at what comes in and what comes out, because it's at steady state, and since there's no reaction, there's no generation and no consumption, so in equals out, and you can do it on moles in this situation because there's no reaction, and since there's no reaction, the moles are going to be conserved as well as the mass. So here we have A coming in from stream 1, A coming in from stream 2, which there is no A in stream 2, A coming in from stream 3, and then A coming out from stream 3, and then A coming out from stream 4, which again, there is no A in stream 4. Taking the SO2 split and the A balance together, we can then do some algebraic manipulations in order to isolate for N3, which we get is 99.01 moles coming out in stream 3, and then we can also solve for Y3SO2, so the stream 3 is going to be 0.00101 of SO2 in it. That's the fraction of SO2 coming out of stream 3. Then we can do a SO2 balance, which is how much SO2 is coming in stream 1, how much SO2 is coming in stream 2. Again, there is no SO2 in stream 2. And then how much SO2 is coming out in stream 3, how much SO2 is coming out in stream 4. We already know all the values except for N4. And we can isolate for M4 and solve it to get 450 moles. And then finally, it's easiest to do a total balance because there's less manipulations involved. And we get, total moles in for stream 1 and stream 2, and then total moles out from stream 3 and stream 4. Isolating for stream 2, which is our last unknown, we get 449.01 moles left. And then the problem asks for what's N2 over N1. And doing that math, we get 4.49 moles of solvent for every mole of gas entering. Be sure to check out chemicalengineeringhq.com. The links to the problem and solutions are down below.